5.1 is called Fundamental Identities. So we're going to learn some main identities to simplify trigonometric expressions. The first question on the homework is a matching problem. We're going to simplify these identities, or we're going to match one of these equivalent expressions to these numbers. For number one, when I need to match cosine x over sine x with something from this box, cosine over sine is always equal to cotangent of x. So I know that I can just write here cotangent of x. This is the definition of the cotangent function. It's always cosine over sine. And tangent function is always equal to sine x over cosine. These are called quotient identity. So sine x over cosine x will be used for tangent of x. Because cosine of x is an even function, so whenever you change your input from x to negative x, this will still generate the same output as cosine of x. Because cosine is an even function, only cosine of x and reciprocal of cosine, which is secant of x. These are the only two even trig functions, and everybody else is an odd function. 1 plus tangent squared x is equal to a secant squared x. This is called Pythagorean identity. When we talk about Pythagorean identity, this is very important in pre-calc class. The main version is sine squared x plus cosine squared x is always equal to a 1. This is called Pythagorean identity, and it is very important in pre-calc class, in trigonometry class. So here, number 5 is going to match with sine squared x plus cosine squared x is equal to a 1. You can derive two other versions of the Pythagorean identity using this main identity. Here's what we're going to do. If I divide everything by cosine squared x in this main identity, if we divide everything by cosine squared x, sine over cosine is tangent, so sine squared over cosine squared x will be simplified as tangent squared of x plus. When you divide the cosine squared by cosine squared, you only get 1. And then 1 over cosine is equal to a secant, so 1 over cosine squared will be equal to a secant squared x. This is called the second form of the Pythagorean identity. So the red one here at the top is the main form of the Pythagorean identity. And from this identity, we can derive the second version of the Pythagorean identity, which is 1 plus tangent squared x, or sometimes it's just tangent squared x plus 1 is always equal to the secant squared x. Instead of dividing everything by cosine squared x, from the main identity, if we divide everything by sine squared x, let's see what happens. So we're still using the main Pythagorean identity, but we are trying to derive different versions of the Pythagorean identity. So now, when I divide everything by sine squared x, sine squared x divided by sine squared x is now 1. Cosine over sine is cotangent of x. So if you divide cosine squared by sine squared x, we're going to get cotangent squared of x. And then 1 over sine is cosecant, so 1 over sine squared x is cosecant squared x. This is the third and the last version of the Pythagorean identity we need to be familiar with. And this is how we do number 2. Number 2 is more matching, more simplifying. So let's take a look at how can I simplify this question 39, which looks like as negative tangent of x. So instead of negative tangent of x, I know that tangent is always equal to sine x over cosine of x. So I copied the negative sign, but instead of tangent of x, I wrote the quotient identity, sine x over cosine x is always equal to the tangent x. And the question now wants me to multiply 10x by cosine of x. So here, the cosine of x and cosine of x will cancel each other, and then this will be simplified as negative sine of x. So from here, this answer is not available, but see, sine of negative x, because sine is an odd function, sine of negative x is always equal to negative sine of x. So the first question here will take the answer of sine of negative x. Question 40 here, we're going to again try to simplify it as much as we can. So I have the cosine squared x minus 1. So if you remember what I showed you before, the main Pythagorean identity sine squared x plus cosine squared x is equal to 1. This is the main Pythagorean identity. If we just divide everything by sine squared x, sine squared over sine squared is just 1. Cosine squared over sine squared is cotangent squared of x. And 1 over sine squared x is equal to a cosecant squared x. So this identity tells me that whenever I see a cosecant squared x, I'm allowed to replace it with 1 plus cotangent squared x. So when I go back to this question, instead of cosecant squared of x, I can write 1 plus cotangent squared of x. And then I'm going to have to minus 1 from this because that's how the question continues. And plus 1 and minus 1 cancels out. And then this just gives me a cotangent squared of x, which is the exact same thing as cosine squared x over sine squared x. So we're going to use this box here as the answer. For the next one here, I am going to look at this one, secant of x over cosecant squared of x, secant of x over cosecant of x. Now, this one, instead of secant of x, I'm allowed to write 1 over cosecant of x because secant and cosecant, they're co-functions. And then we're going to divide it by the cosecant of x. So when I need to simplify this, copy the first one, multiply it by the reciprocal of the second one. 1 times 1 is 1. Cosecant times cosecant is just cosecant squared x. So this is going to be 1 over cosecant squared x will be copied for question 41 here. Next one here is 1 plus sine squared x. Let's see what we can do here. 1 plus sine squared of x. Because this looks like more complicated, let's try to actually simplify it here. So if you look at the main Pythagorean identity, sine squared plus cosine squared x is equal to a 1. Here, in order to get the secant x, secant is 1 over cosine, right? 1 over cosine. So I'm going to just divide everything by cosine squared x here. So sine squared over cosine squared is just tangent squared x. And then this is plus 1, and this is secant squared x. So when I see a secant squared of x, I'm allowed to replace it with 10 squared x plus 1. So I'm going to replace this with 10 squared of x plus 1. And then the question continues with minus 10x squared plus sine squared of x. And then this cancels this. And then we end up with 1 plus sine squared x, which is what we have in the problem. So this one is going to use the equivalent of secant squared x minus 10 squared of x plus sine squared of x. And here, sine squared x, I need to write an equivalent to this one, sine squared x. For this one, sine squared of x, let's just open some space here. And then I'm just going to actually do this. More. So let's see, which one did we use so far? Which one did we not? This one, I replaced it with sine over cosine, and this was the same thing as sine of negative x. This one, cosine squared x minus 1, I believe I remember this one was for question 3. It says that write this expression in terms of sine and cosine. So in terms of, instead of cotangent of x, we can write cosine of x over sine of x. And then this cotangent of x is getting multiplied by sine of x. So the top sine of x and bottom sine of x cancel out. And then the final answer will be just cosine of x for this question. Now we need to simplify question 4. And the problem we have is cosecant of theta times cosine of theta times tangent of theta. Whenever I have these questions, I like to write everything in terms of sine and cosine. So instead of cosecant of theta, I can write 1 over sine of theta times, instead of cosine of theta, cosine, I'm just going to write cosine of theta because this is like a main function. And instead of tangent of theta, I can write sine theta over cos theta. Now we're going to see if we can simplify anything. The top cosine theta cancels the bottom cosine theta. The top sine theta cancels the bottom sine theta. That means everything cancels out. We're going to end up with a 1 for question 4. For question 5, now we want to simplify cosine of x times cosecant of x. So cosine of x, I just copy it because it's simple enough. But instead of cosecant of x, I can write 1 over sine of x because this is the equivalent expression for cosecant of x. It's always equal to 1 over sine. So at the top, cosine x times 1 is just cosine of x. And at the bottom, we have sine of x. And cosine divided by sine is always equal to the cotangent of x. And this is how we're going to do question 5. For number 6, we want to simplify this expression so that it matches. There's more options here. So let's just see what we can do here. Since main identity is sine squared of any angle plus cosine squared of any angle is equal to 1, because I see a cotangent squared theta here. And in order to get a cotangent square, I'm going to have to divide everything by sine squared theta here to get the another version of this Pythagorean identity. The sine squared over sine squared is 1. Cosine over sine is cotangent, so this will return a cotangent squared of theta. And 1 over sine squared is just cosecant squared theta. But here actually, there is probably an easier way. Let's just redo this, start over. So what I would like to do is, instead of using the Pythagorean identity here, I want to keep my negative sine squared theta in the problem. And then I am going to keep the negative 1 for now. But instead of cotangent squared theta, we can write cosine squared theta over sine squared theta. Because cosine over sine is just cotangent, but because it's cotangent squared, we need the squared version of each one. Now I can do the distribution property. Negative sine squared theta and negative 1, when I multiply it, it's just positive sine squared theta. And then negative times negative is again positive, but sine squared theta is going to cancel the bottom squared theta, and I'm just going to get cosine squared theta when I distribute this. Now, this will just simplify to a 1 because this is called Pythagorean identity. Sine squared plus cosine squared is always equal to a 1. It doesn't matter what the angle is. Now, for the next question, we want to simplify this. I'm going to again just FOIL this, multiply everything. 1 will be multiplied by 1, which creates a 1. 1 will be multiplied by negative cosine of theta, so that's negative cosine of theta. Now I'm going to multiply secant theta by 1, which is just secant theta. And then we're going to multiply positive times negative is negative, and I'm going to multiply secant theta by cosine of theta. So I have a secant theta times cosine theta here after I FOIL these two binomials. How is this going to help me now? Let's see, what can I simplify? Here, I see right away that secant theta can be rewritten as 1 over cosine of theta. And I need to multiply this by cosine of theta. I'm just going to bring down everything for now to see if anything cancels out so far. When I replace the secant theta by 1 over cosine of theta, the cosine of theta at the top and the cosine of theta at the bottom, they will cancel out. And I will get 1 minus cosine of theta plus secant of theta minus 1. So here, positive 1 and negative 1 will cross out. And I am going to end up with this expression. And if I write the positive term first, that's secant of theta, and then I want to write the negative term after this, my expression simplifies to a secant of theta minus cosine of theta in this problem. Number 8 is another simplification problem. It says that write them in terms of sine and cosine first, then simplify so that no quotients appear in the final expression. So cosecant of beta can be written as 1 over sine of beta. And then there's also another sine of beta here. In order to subtract two things, they have to have the denominators matching. So since sine of beta have a denominator of 1 right now, and we cannot perform this subtraction because they don't have the common denominator yet, we're going to go ahead and multiply the second part by sine of beta. So I will copy the first part the same, 1 over sine of beta. And then here, sine of beta multiplied by sine of beta, which makes sine squared of beta. And the denominator will be just a sine of beta now. Now the denominators are matching, so I can write them as one single fraction. The top is 1 minus sine squared beta. The bottom is just sine of beta. 1 minus sine squared beta is always equal to cosine squared of beta because of the Pythagorean identity. We know that sine squared plus cosine squared is always equal to a 1. So 1 minus sine squared beta is always equal to the cosine squared beta. And then this is my sine beta. Here, we still have a denominator going on, and they don't want a denominator. So I'm going to rewrite this as cosine of beta times cosine of beta, and the denominator is sine of beta. Now, this part, cosine over sine, can be simplified as cotangent of beta. That means I have a cosine of beta here, and then this is the cotangent of beta. This is how I can simplify this expression without a denominator. Now for question 9, we will be simplifying this expression, write each of terms in terms of sine and cosine, then simplify, no quotients appear in the final expression. Okay, so let's not listen to them. Let's first FOIL, then simplify. So secant of theta times cosine of theta. That's the first thing I'm going to get when I go ahead and distribute it. Okay. And then secant theta times sine theta. Secant of theta times sine of theta. Now here I'm going to get negative cosecant theta times cosine theta. And finally, negative times positive is negative. And I'm going to get cosecant theta times sine of theta. Okay. The secant is, now I'm going to go ahead and replace everything if it is possible. Instead of secant, I can write 1 over cosine of theta. And then this is just a cosine theta. Instead of secant, I can write again 1 over cosine of theta times sine of theta here. Instead of cosecant theta, I can write 1 over sine of theta times cosine of theta. Instead of cosecant theta, I can write 1 over sine of theta times sine of theta. Now what happens is the top cosine of theta cancels the bottom of cosine theta. So we will just get 1 here from this part. And then here we will have 1 times sine of theta over cos theta. So that's sine over cos. And that returns a tangent of theta here. So this part will return a tangent of theta. Minus, because the next term starts with a minus. Cosine over sine again, and cosine over sine is cotangent of theta. And then top sine theta cancels the bottom sine of theta, and that's just a 1. Positive one and negative one cancels out, and this is what we end up at the end. This question will return me a tangent of theta minus cotangent of theta as an answer in this question. For this one now, again, they recommend that we should convert everything to sine and cosine first and simplify. Let's do that this time. The question starts with a sine of x. Instead of cosecant of x, I can write 1 over sine x and then minus sine of x. That's what the question is. I would like to go ahead and distribute sine x over 1 over sine x. The sine x at the top and sine x at the bottom cancel out, and we just get 1. And then sine x times sine x is, so it will be connected with a minus. Sine x times sine x is sine squared x. And 1 minus sine squared x is always equal to cosine squared x because of the Pythagorean identity. For question 11, this is the question we get. Write each expression in terms of sine and cosine and simplify. Instead of secant squared, I can write 1 over cosine squared theta minus 1 all over. Instead of cosecant squared x, I can write 1 over sine squared theta minus 1. Here, in order to subtract them, they have to have common denominators. Since they don't, I'm going to do a magic. I'm going to rewrite the 1 as, cosine squared theta over cosine squared theta. So when we divide cosine squared by cosine squared, that's still 1, but this time the denominators are actually matching. This allows me to write them together. So at the top, I will have just 1 minus cosine squared theta all over cosine squared theta because they have a common denominator of cosine squared theta. I'm going to do the same magic here. Instead of 1 this time, I would like to write sine squared theta over sine squared theta. So when you divide sine squared by sine squared, it's still 1. However, when I replace the 1 to this format, they are matching, the denominators are matching this time. So it allows me to write it as 1 minus sine squared theta all over sine squared theta. Okay. Now, more simplification. 1 minus cosine squared theta is always equal to sine squared theta because of the Pythagorean identity, divided by cosine squared theta. And then 1 minus sine squared theta is always equal to cosine squared theta over sine squared theta. To simplify this, we're going to copy the first one. And then we're going to multiply it by the reciprocal of the other one. This will return sine to the 4th power at the top, and then the bottom will be cosine to the 4th power. And sine over cosine is always equal to tangent. So this question is going to just return us tangent to the 4th power of theta, because sine over cosine is tangent, because both of them are 4th power. So this will be just equal to the tangent to the 4th power of theta for question 11. The last question on the homework is, there's a video that you should click and watch before you do this homework. It's very similar to another one we did. Probably you will watch the video to learn of this concept more, but let's practice this one more time. I have a negative sine squared theta, and I'm going to multiply it by 1, so I will still get the same expression. Negative times negative is positive. And next time, I'm going to get sine squared theta times cosecant squared of theta when I distribute sine squared theta over this parentheses. I'm going to copy the first part. But here, I will again copy the sine squared theta, but instead of cosecant squared theta, I can write 1 over sine squared theta. So this one cancels this one. I'm just going to get negative sine squared theta plus 1 as an answer. When I continue to simplify this, I will keep this one with me, but I know that instead of 1, I can still write sine squared theta plus cosine squared theta. because sine squared plus cosine squared is always equal to 1. This allows me to cancel the negative sine squared theta with positive sine squared theta. So I'm just going to end up with cosine squared theta as a final answer for question 12. And this is what you're going to do for 5.1 when we say trigonometric identities.